In this episode, we're going to make cloud networking feel less like a fog of mysterious boxes and more like a map you can actually read, even if you have never designed a network before. Cloud platforms hide a lot of physical complexity, but they still rely on familiar networking ideas like address ranges, routing decisions, and controlled entry and exit points. The challenge for beginners is that the cloud wraps those ideas in new names, new defaults, and a few behaviors that do not match what you might expect from a home router. When you understand the primitives, meaning the basic building blocks, you can predict how traffic will move and why a system can or cannot reach another system. That ability to predict is a security skill because most cloud security failures involve unintended reachability, not dramatic movie-style hacking. By the end, you should be able to picture the network layout in your head and explain, in plain language, how a packet finds its path. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at CIDR.News in the Bare Metal Study Guide series. A good starting point is to treat cloud networking like building a private neighborhood inside a huge shared city. The city is the cloud provider's global infrastructure, and your neighborhood is the isolated area you control. In most clouds, that private neighborhood is called a virtual private cloud, VPC, or a virtual network, VNET, and those are the core containers where your private address space and routing rules live. People sometimes hear the word virtual and assume it means less real, but the impact is very real because the VPC or VNET defines who can talk to whom and how traffic can enter or leave. This is where you decide the address range, the segmentation boundaries, and the default posture of connectivity. When you create resources like servers or databases, they are not just floating in the cloud. They are placed inside this network container. If you can picture the VPC or VNET as the walls of your neighborhood, the rest of the primitives start to make more sense. Inside that network container, the next primitive to understand is the address space, which is usually expressed as a classless interdomain routing, CIDR, block. A CIDR block is simply a way of saying which internet protocol, IP, addresses belong to your network, and it is the cloud version of choosing how big your neighborhood is. Beginners often treat this choice as a formality, but it affects everything from how many systems you can place in the network to how easily you can connect multiple networks together later. If you pick an address range that overlaps with another network you need to connect to, you can create painful routing conflicts that are hard to fix after the fact. It also helps to understand that most cloud VPC or VNET designs use private IP ranges, meaning addresses that are not directly reachable from the public internet. That private address plan is the starting point for controlled connectivity, not an automatic promise of safety. Once you have an address range, cloud networks are typically divided into subnets, which are smaller slices of that address space used to group resources. Subnets are often tied to availability zones, which are separate data center locations within a region, and this is one reason cloud networking can feel different from a small on-premises network. The subnet becomes a placement boundary as well as a routing boundary because resources are launched into specific subnets, and those subnets inherit certain routing and access rules. Beginners sometimes assume a subnet is automatically public or private, but in cloud environments, public or private is usually a behavior created by routing choices, not a label you toggle. If a subnet's route table sends traffic to the internet through a gateway, it behaves like a public subnet, at least in terms of outbound and inbound pathways. If the subnet routes remain internal, it behaves more like a private space. Thinking this way helps you avoid the common mistake of assuming naming conventions provide security. Routing tables are the part that turns a static map into a system with directions, because routing is simply the logic that decides where traffic goes next. A route table contains rules that match destination address ranges and point to a next hop target, such as staying local, going to a gateway, or going to another network. Beginners sometimes expect routing to be magical and automatic, but in cloud networks, routing behavior follows clear, deterministic rules. When a resource sends traffic to an address, the network checks the route table associated with the subnet and chooses the best match. Best match usually means the most specific route, often described as longest prefix match, where a more specific destination range wins over a broad default. This detail matters because you can have a safe, specific route for internal services and still keep a general route for other traffic, and the network will choose correctly if the rules are set up well. If the rules are wrong, the network will still behave correctly, just not the way you intended. To understand how the public internet fits into this, you need to recognize that cloud networks use explicit gateways rather than assuming everything is internet connected. An internet gateway is a managed component that allows resources with appropriate addressing and rules to communicate with the internet, and it sits at the boundary of your VPC or VNET. Beginners often believe that attaching an internet gateway automatically exposes everything, but exposure still depends on routing and on access controls that permit inbound traffic. What the gateway really does is create the possibility of internet reachability, which can be a necessary feature for public-facing services. A separate concept is a network address translation, NAT, gateway, which is typically used to allow private resources to initiate outbound internet connections without being directly reachable from the internet. This is a powerful primitive because it supports common security goals, such as letting servers download updates while keeping them non-public. When you can explain the difference between Internet Gateway and NAT Gateway, you are already thinking like a defender. Beginners also need a clear mental model for what it means for a resource to have a public IP address, because that phrase can be misleading. A public IP address makes a resource addressable from the internet, but addressable does not mean accessible, because accessibility still depends on firewall-like controls. In many cloud designs, you want only a small number of entry points to be public, such as a load balancer, while keeping databases and internal services private. That design relies on routing that supports internal reachability and on rules that restrict inbound access. A frequent misunderstanding is thinking that if something is in a private subnet, it is automatically safe, but private only describes the absence of direct internet routing, not the absence of internal risk. If an attacker compromises one internal system, private subnets do not stop lateral movement by themselves. The network design needs intentional segmentation and controls, which is why understanding primitives is not just networking trivia. Another routing behavior that becomes important as environments grow is how networks connect to other networks, because very few real cloud setups stay isolated forever. You might connect a VPC to another VPC, connect to a corporate network, or connect across regions, and each of those connections introduces new routes and new possibilities for unintended reachability. Peering is one common pattern, where two networks are connected directly and routes are exchanged so traffic can flow privately between them. Beginners sometimes imagine peering as a simple cable, but it behaves more like a negotiated relationship with limits, and it can create complex graphs of connectivity if done without planning. There are also hub-and-spoke patterns, where a central transit component connects multiple networks in a controlled way, and that can simplify routing and security if designed carefully. The key point is that every connection adds routes, and every route is a promise that traffic is allowed to go somewhere. Defenders learn to treat routing changes as security changes. When people say cloud routing is simple, they usually mean the cloud provider manages the underlying infrastructure, not that your routing decisions are automatically safe. Routing mistakes in the cloud tend to fall into a few patterns, and recognizing them helps you troubleshoot and prevent them. One pattern is accidental broad routing, where a default route sends traffic to a gateway when it should have stayed internal, creating unexpected exposure. Another pattern is missing routes, where systems cannot reach a dependency because the route table does not include a path to the destination range. A third pattern involves overlapping address spaces, where two networks use the same private ranges and routing cannot distinguish them correctly. Beginners often assume that if connectivity fails, the issue must be a firewall, but routing is just as likely, especially when multiple networks are involved. When you can ask, what route would this traffic take, you shift from guessing to reasoning. That shift is exactly what investigations and secure design require. It also helps to understand that routing decisions happen before higher-level security controls can matter, because the network must know where to send traffic even if it will later be denied. This is why defenders care about routes as a form of blast radius management. If there is no route between two subnets, then traffic cannot flow at all, which is a strong form of segmentation that does not rely on perfect firewall rules. If there is a route, then the question becomes whether controls permit that traffic, and controls are easier to misconfigure than the absence of a route. Beginners sometimes build networks that are fully meshed because it feels convenient, and then they try to rely entirely on fine-grained rules for security. That approach can work, but it increases complexity and increases the chance that one overly broad rule creates a big problem. Good cloud networking often starts by limiting reachability through routing design and then refining access through additional controls. Routing is the skeleton, and security rules are the muscles, and you want both to be intentional. Cloud platforms also introduce the idea of implicit local routing inside the VPC or VNET, where traffic between subnets in the same network container is typically allowed to route by default. That does not mean it is permitted by access controls, but it does mean the path exists, and that can surprise beginners who expected subnets to be isolated by default. This is why subnet design is often paired with specific route table associations and carefully planned segmentation, rather than assuming subnets alone create barriers. Another important behavior is that some managed services sit outside your subnets but are reachable through special networking constructs, which can make it feel like traffic is teleporting. When you encounter that feeling, the safest move is to return to primitives. What is the source? What is the destination? What route table applies? And what gateway or endpoint makes the path possible? Even when the cloud adds abstraction, the underlying logic is still consistent. A practical way to connect all of this to security is to think about attacker movement as a networking problem as much as it is an identity problem. If an attacker compromises a workload, the next question is what that workload can reach, because reachability determines what can be probed, exploited, or accessed next. Routing defines reachability at a coarse level, and segmentation decisions can dramatically reduce what is reachable even if credentials are stolen. Beginners sometimes focus only on preventing compromise and forget that containment is a major goal too. Network primitives like subnets, route tables, gateways, and private connectivity patterns are containment tools when used well. When routing is tightly controlled, attackers have fewer paths for lateral movement, fewer opportunities to discover services, and fewer easy routes to exfiltrate data. That does not eliminate risk, but it changes the shape of the battle in your favor. Cloud networking is not separate from cloud security. It is one of its most powerful levers. As environments span accounts and regions, another beginner challenge is keeping the mental model coherent when the same primitive appears in many places. The trick is to standardize naming and design patterns so that when you see a subnet, you can infer its purpose, and when you see a route table, you can infer its intent. Even if you are not building anything yourself, being able to read the design is essential for investigations. When something suspicious happens, responders often need to answer whether a path existed, whether it was intended, and whether it changed recently. That is why control plane logs and network design go hand in hand, because routing changes are configuration changes with security impact. A mature cloud network does not depend on everyone remembering every rule. It depends on patterns that are predictable and verifiable. Normalization of logs, centralized visibility, and consistent network primitives all reinforce each other. The more consistent the primitives, the easier it is to detect deviations that matter. By this point, the core message should feel clear. Cloud networking primitives are the vocabulary you need to describe reachability, and routing behaviors are the grammar that turns that vocabulary into actual movement of traffic. A VPC or VNET gives you the private neighborhood. CIDR blocks define its size. Subnets organize placement and scope. Route tables define direction, and gateways control the boundaries between private space and the broader world. Once you can reason about longest prefix match, default routes, and explicit connectivity patterns like peering and transit, you can predict outcomes instead of discovering them by surprise. This predictive ability is what makes secure design possible, because security depends on controlling what can reach what, not merely hoping rules are correct. Beginners often feel intimidated by networking because it seems abstract, but cloud networking becomes manageable when you anchor it to these primitives and ask simple, consistent questions about paths. When you keep that discipline, you are far less likely to create accidental exposure, misroutes, or hidden trust relationships.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.